In this video, we're going to take a look at the trend of ionization energy. So let's go take a look at what ionization energy is, and we'll also take a look at what the trend looks like in the periodic table. So here we go. So ionization energy, when we define it, it's the energy that's required to remove the outermost electron from an atom or an ion when it's a gas. So let's look at this example over here. Here we have an atom, and we're going to assume it's sample of it in gas state. And you want to remove an electron. To remove an electron, it takes energy to do that. So if I want to remove this electron over here, it'll have to put in some energy. It's like I have to pay the atom to take its electron away. And so the amount of energy it's required to do that, that's called the ionization energy. So here we have our generalized equation for the ionization energy. You'll notice here we have the atom. So this A means just some sort of atom plus energy. So the ionization energy and an arrow. When we put the energy in, it's going to remove the electron and then result in an atom with a +1 charge. So the first electron you remove adds +1 charge. You could remove more, but right now we're talking really about something called the first ionization energy. So the energy required to remove sort of that first electron from the outermost shell. And then if you have to remove more, there's something called second, third, fourth ionization energies as well. But generally, what we see is, you can look at our arrow over here. Ionization energy is generally smaller on the left side and then gets larger as you go towards the right side. So we increase from left to right. And the reason for that is because, remember, as you go towards the right side, you have more protons, and so you have a larger effective nuclear charge, same number of shells, and you hold on to the electrons more tightly. So you have to put more energy to rip the electron away, since the electrons are being held more tightly by their more powerful nucleus. So that's why typically non-metals will have a higher ionization energy than metals. It takes a lot more energy to take away an electron from a non-metal than it does from a metal. Remember, metals tend to lose electrons when they're doing a reaction to make an ionic compound, and that's because their ionization energies are pretty low. So lithium has a very low ionization energy, or sodium has a low ionization energy compared to chlorine. So sodium would give away its electrons to chlorine. The other trend you might notice is that ionization energy will actually decrease as you go down a group. And what that means is you need less energy to take away the electrons as you go down the group. So more energy to take away an electron from lithium, a little bit less to take it away from sodium, less to take it away from potassium. And the reason that is because of the shielding effect and the distance from the nucleus. So for example, the valence electron for potassium is farther away from the nucleus than the valence electron for lithium, because there's more shells in potassium. So you don't have to put as much energy to take the electron away, since it's so far away from the nucleus to begin with. So generally, as you go from the top to the bottom, the ionization energy decreases. In other words, when you're drawing your arrow, the arrow will point towards the top. And that's because it increases as you're towards the top. And then the head is the top, and the tail is the bottom because it's lower there. Since these shells are so far, there's so many shells, the electrons are so far away, you don't have to put much energy in to rip the electrons away. This graph here is the ionization energy plotted on a graph. So on the x-axis, you can see the atomic number, and on the y-axis, you can see the ionization energy over here. And so when we say atomic number, you literally take the atomic number from the periodic table. So, element number 1, number 2. So number 1 over here would be hydrogen, and number 2 is helium. Then you can say, lithium, and you can continue like this. So beryllium, boron, so on and so forth. And so you can see element number 10 is neon. And so what you'll notice is, as you go from hydrogen to helium, the ionization energy increased because you went from left to right. Let's take a look over here. As we go from lithium, so this is element number 3, lithium to neon, the ionization energy overall, the trend, there's some little exceptions here and there, but for the most part, the ionization energy goes up because you're going from left to right, And then over here, this would be our next metal, because this is neon. So right after neon, we have sodium. So as you go from sodium to argon, the ionization energy goes up because you're going from left to right. But what I want you to also notice is that there is a little bit of a trend happening with the period. So overall, the ionization energy, for example, of these elements here would be in the third period, and these elements here in the second. The third period ionization energies overall for a corresponding element below it are generally lower because you have more shells happening. So, for example, over here we have, well, let's just say, let's compare these ones and these ones over here. So this was neon. So that means this metal over here is sodium because it's right after neon. This is argon. And so this metal over here is potassium because it's right after argon. And so if you compare sodium and potassium, potassium has a lower ionization energy than sodium. And that's because, again, there's more shells. But the general idea is that you have your increase across the group happening there. Same thing, sorry, across the period happening here, 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 here. So those are all increases across the periods that are happening. And you can see there are some minor exceptions here and there, but we're going to focus on the overall trend currently happening. So this here is the graph for ionization energy and atomic number. You can spot those trends on that graph. What I would do if I were you is practice being able to spot, which element would be which. So even though they're not all labeled here, could you know that this is helium? So after helium, after atomic number 2, we're at atomic number 3 over here, which is lithium. So now we're in here, and then now we're going to beryllium, and then boron, and then carbon, and nitrogen, and oxygen, and fluorine, and then neon, for example. And after neon, we're going to, that was element number 10. So now we're going to element number 11, which is sodium, then magnesium, so on and so forth. Okay, so even though, yes, there's some minor exceptions with a little bit going down, overall, it's going up. It's going up across the period. So increasing ionization across period, and then decreasing ionization as you go down, right? So from, let's say, sodium over here to potassium. Potassium has a lower ionization energy. So we're going to go ahead and take a look at these questions here. So you can try this yourself. You can pause the video, try the question yourself, and then come back to it afterwards and see if you are on the right track. So why are noble gases at all the peaks in figure 1.19? So notice the noble gases are all at the peaks. So how come the noble gases have the highest ionization energy within their sort of periods? And so the idea is that within their periods, the noble gases have a greater effective nuclear charge, and so hold on to the electrons more strongly and require more energy to remove those electrons from their valence shell. So that's why they have a higher first ionization energy within their period. So that really represents the period, and this is more towards the right, more effective nuclear charge. All these elements here have the same number of shells, and so would neon, but it has a greater effective nuclear charge. Then why are all group 1 elements at the lowest point? Well, you'll notice that all the group 1 elements are always at the lowest point in their period. And that's because they're on the left side of the periodic table. And what that means is they have the fewest number of protons in their nucleus, in their period. So they have the lowest effective nuclear charge, and that's why you can easily rip away their electrons compared to something that would follow them in their period. So I just want to make sure I said that. So noble gases are at the peaks because within their period, the more towards the right, they have a greater effective nuclear charge because they have more protons to hang on to the electron, so it takes more energy to rip the electron away. Whereas the alkali metal are at the lowest parts, the lowest points, because in their period, they're all the way to the left. They have the smallest number of protons in their period, so they have the smallest effective nuclear charge. They can't hold on to the electrons as strongly, and so it doesn't take as much ionization energy to remove the electron. So we can go ahead and take a look at if we understand this concept by doing a few practice problems together. So which do you expect to have the highest ionization energy? Fluorine, nitrogen, or helium? And so let's go ahead and take a look at those problems. First, we're going to fill in some blanks, and then we'll do some more of those problems together. So here we are, first ionization energy. The amount of energy required to remove the outermost electron from the atom or ion in its gas state. And so if you want to write a general equation for the ionization energy, the first ionization energy, we need to remove the first electron there. You would write the atom in the gas form plus energy, and then you would write the ion now charged. Since you're only removing the first electron, you're just going to put a +1 charge. That's +1 really. So I don't have to put +1, but I will now just to show you it's 1. And then plus the 1 electron that was removed. So this is 1 electron being removed. I just didn't put a coefficient of 1 there. But that's the first ionization energy. So for example, I might do like this. I could write, I could do sodium in its gas state. You're putting in some energy. So energy, that would be ionization energy. And then when you do that, it's going to become the sodium ion. And then plus the electron that was removed. And so that would be the ionization equation for sodium, for the first ionization energy. And so one of the trends that we saw for ionization energy is that going from left to right, so going from this side to this side, the ionization energy tends to increase. So increases from left to right. And we saw that that was because there's a greater effective nuclear charge towards the right. There's more protons to hold the electrons down. So it takes more energy to rip the electron away. Nonmetals, as a result of that, since they're towards the right side and have a lower effective nuclear charge than the metals, will have a lower ionization energy than metals. So it's easier to rip away electrons from nonmetals. They'll have a higher. That was wrong. I meant to say the opposite. Nonmetals, because they're towards the right, they have a higher effective nuclear charge. And because they have a higher effective nuclear charge, they have a higher ionization energy than metals. So I misspoke earlier, my bad. And so it's harder to rip away electrons from the nonmetals, but easier to rip electrons away from the metals just because you don't need as much energy to rip it away from the metals. Ionization energy going down a group, we saw tends to decrease. So decreases going down a group from top to bottom. And the reason for that is that there are more shells, greater distance from the nucleus, so there's a weaker hold on the outer electrons, which means that you don't need as much energy to rip them away. So that's why, for example, francium over here would have a lower ionization energy than lithium over here because there's so many shells in between the nucleus and the outer electron. And then we saw how to read this graph for ionization energy and an atomic number. Let's go ahead and do some practice problems together. So we already did these practice problems here. I answered it verbally on the slide deck, so you can go ahead and take a look at that and write it out as I mentioned it and try to summarize it yourself. But let's go ahead and try a practice problem like the one we see in this box over here. So which would you expect to have the highest ionization energy, F, N, or He? So let's find those in our periodic table. So here's F, here's He, and here's N. So between N and F for ionization energy, it looks like F would have higher ionization energy than N. So that would have the first ionization, that would have a higher one than N. But now we're looking at between He versus F. Now the reason that F has a higher ionization energy is because it's more towards the right side, and as we know, we increase towards the right. Now, if we look at helium, we could look at our trend this way. Helium is more towards the top, and towards the right as well. So our ionization energy increases as you go up, but also to the right. So this is to the right and toward the top of fluorine. So as a result, helium should win because helium is to the right and the top, and that wins in both cases of those trends. So helium should have the highest ionization energy between fluorine and helium. And if you look at our graph over here, I think that makes sense. So here's helium with its ionization energy. And then if you look for fluorine, so lithium, and then beryllium, and then boron, and then carbon, nitrogen, oxygen, fluorine, notice that helium is on top there with its ionization energy there. So why does fluorine have a higher ionization energy than iodine? So here's fluorine and here's iodine. So there's two ways you can answer that question, or two things or parts I'm looking for in your answer. So first of all, I'm looking for fluorine is higher up in its group. So this is answering based on PT location, on periodic table location. That's what you're answering that based off of. But the second part is explain it with atomic structure. Explain it with atomic structure. To explain it with atomic structure, well, fluorine has fewer shells, therefore the nucleus holds on to the valence electrons more effectively. And so that requires more energy to rip away the electron. Iodine has more, you could have also said iodine has more shells, and because of more shielding, it does not hold on to the electrons as effectively. So you could have also said it that way as well. But the idea is that you explain it with periodic table location and also the atomic structure part, where you might talk about the shielding and shells, or you might talk about the effective nuclear charge. So let's take a look. Which one in each pair would have the greater ionization energy? So greater means larger. So between lithium and beryllium, beryllium, because it's more towards the right, and it has therefore a greater effective nuclear charge holding that electron, so you need more energy to rip it away. Calcium or barium. So here's calcium, here's barium. Greater would be calcium, because calcium's higher to the top. Barium's lower on the group. So if barium has more shells, and so the protons aren't holding onto the electrons as tightly because the outer electrons are farther away. And so you don't need as much energy to remove those outer electrons. Between sodium and potassium, well, so potassium is lower down, so it has a lower ionization energy. Sodium wins in this case for the similar reason that we saw in question B. Between phosphorus and argon, well, argon's more towards the right, greater effective nuclear charge, so argon has a higher ionization energy. Between chlorine and silicon, similar reasoning, chlorine has the higher ionization energy. And between lithium and potassium, similar reasoning, lithium has a higher ionization energy. And so that is a trend of ionization energy. We saw how to write some equations for ionization energy, the first ionization energy, and we saw how to identify the trend in the periodic table and to explain that trend in the periodic table. And we also saw how to read the graph for ionization energies. We're just going to finish off this video by taking a look at successive ionization energies. So the first ionization energy was removing that first outer electron, but there's more electrons you can move. If you put in more energy, you can rip away more electrons. And so those would be called successive ionization energies, being able to remove the other electrons, the ones that come next. So, for example, the second ionization energy is the amount of energy needed to remove the next outermost electron from the ion. So you'll remove the first one, and then remove another one after that, and remove another, and another, and another, and another. And so you can have ionization energies for as many electrons as are present. So you can have a third, fourth, fifth, nth, where n is the number of electrons. Okay? So in general, when you're writing out your equation for the ionization energy, as we saw, the first one is you just kind of do your gas element plus the energy, and then afterwards you have your ion plus the electron. That's the first one. Now, if you're doing your second one, you take your ion that you had in the product of the first one here, you add more energy, and then that results in your A now 2 plus, because you removed another one from the plus another electron coming out. So that would be, for example, for the second ionization energy. And you can continue this. You can say, okay, I'm going to take the A 2 plus, and I'm going to add more energy to remove another electron. And then you would have now a 3 plus another electron being removed. And this would be the, for example, the third ionization energy. And so there is a trend that happens with this, the first, second, third, fourth. Generally, each successive ionization energy, so as you do more and more, as you remove more and more electrons, is larger. So it takes more energy to remove the second one, and then even more to remove the third and the fourth. And so the reason for that, if you think about it, is that it just takes more energy to take electrons from a more positive ion, right? When you remove the first electron, you become A plus. And so now to remove an electron from something that's positive, that already lost something, is going to be a bit harder. You're going to have to put more energy in because you have a positively charged ion at this point. And then if you have A2 plus, that's holding on to the electrons that it has left even more, right? It's afraid to lose more. So you have to put even more energy in and more energy in. It just gets worse and worse and worse and worse and worse. So if you have, the fourth, that takes even more energy to take away the remaining electrons. So the way to kind of think about it is, here you have somebody watching a bank, and here you have someone who's going to steal some money. So to steal the money that's way over here, this person doesn't need to worry too much or sneak around too much. It's far away from the security guard. Um, and so that would be kind of like having a low ionization energy. You just walk there and take it. But now the security guard noticed, and there's a little bit of money left steal. So this is a bit riskier. This thief has to maybe sneak around a bit, run a little bit faster, and take it because the security guard's really close by. And if you steal both of these, if both of these are gone, now you only have this left to steal. The security guard has to really sneak around, really run fast, really grab it, really run away fast. So it's a lot more work to do that since the security guard is really close to these remaining ones and is really, really afraid to lose any more. So it takes a lot more work on the behalf of this thief over here to actually do that. And so that's kind of the reason why the successive ionization energies work as they do. Um, and so if we go to our little presentation over here, you can see that concept happening in the picture here. And let's take a look at an example specifically for aluminum. So here we have the ionization energies for aluminum. So if you take a look, we have the first, second, third, fourth, and here are the equations written out. We should also write gas every single time for each one of these because it does happen in the gas state. So I will go back and add that to the note. But the idea that you can see here is that the ionization energy is going up every single time. So it takes energy to remove the first one, and the second electron, and the third electron. And look at that. So it goes up and up and up. It is a big jump, but look at the jump from the third to the fourth. That's a huge jump. So think about, if you look at the periodic table, aluminum will most likely form an aluminum 3 plus ion when it does form ions in reactions. It forms that. But why wouldn't it form a 4 plus? Why? I mean, technically it could, but why would it rarely do that, if ever, based on this example here? So think about it a bit. Try to write out a little response, and then you can pause the video, and then you can see if you're on the right track. So the reason that aluminum 4 plus would probably not form at all is because the ionization energy is just too high to form that. Yes, it's pretty high for the Al3 plus, but it's not that much of a jump from 2 to 3. To go from the third to the fourth, to remove one more electron from 3 plus, takes way too much energy, and there's probably not that much energy available for that to happen. So that's why the aluminum 4 plus ion probably doesn't form, but something like 3 plus does form, because that is typically going to be available in the environment, but not the 11,600 kilojoules. You might not know what this mole is yet, but just think of this as a unit of energy at the end over here. So let's go ahead and try a practice problem out. And as I mentioned, do write in your equations, make sure that everything is in the gas state as it's supposed to be. So I will add that and fix that. So when you do see the note, you'll have it along these lines here like this. When the gas state. That's by definition what happens. So let's go ahead and do some practice problems with ionization energies. Just to show you over here a couple examples before we do some practice problems actually. So we did the ionization equations. Make sure you show the gas state. And you usually should label what the ionization equation is. So first, second, and every time you lose an electron, you become more and more positive as you write out those ionization equations. And over here we can see our first ionization energy. We're just removing the first outer electron. So Na gas plus the ionization energy produces Na plus and one electron. And so you can do that for a variety of different elements. It's good to take a look at the aluminum one because it's a good example of several ionization energies. So let's go ahead and arrange the following according to increasing ionization energies. So basically what this means is from smallest to biggest. So the one that you can take away electrons from the easiest would be magnesium. It has lowest ionization energy because, well, it's not positive. It would be the first ionization energy. The one that would be the hardest would most likely be the magnesium 2 plus because it's the most charged. And then after that, and then in between we did magnesium plus. So magnesium would have the smallest ionization energy, and the magnesium plus would be in the middle. And magnesium 2 plus would be have the highest ionization energy. And we already explained why Al4 plus isn't formed. We did that verbally in the slide deck, so you can go ahead and try to summarize that yourself. Just a reminder to make sure that you include the gas state in your equations because that's how these reactions actually happen. So this would be in a gas state, this would be in the gas state as well, and that's how that would occur. And as you can see, it's written in the gas state over here as well. So do practice writing out ionization equations. You can see the general equation written out for you over here. So we can do an example together just to finish off. So magnesium will lose 2 electrons to become isoelectronic to neon. And so the net overall charge would be +2. So to show that process of magnesium becoming magnesium +2, we would show the first ionization energy. So we would show, for example, magnesium, you're adding energy to remove an electron, it would become magnesium plus gas state, and then plus electron over here. And then you would show the second ionization energy. So you would show, for example, magnesium plus in the gas state, and then plus energy being added to remove another electron, and that would form your magnesium 2 plus in its gas state, plus the other electron that you just removed. And so that's the second ionization energy. So as you can see, we lost overall 2, which is why my Mg plus 2 would be +2 at the very end. So those are all the skills that you need to know for ionization energy. Make sure you look at the graph. Make sure you can summarize your ionization energy on the periodic table with arrows as well. As you can see at the start of the lesson, we had one where we summarized all the different elements, different trends. And so you can see ionization energy goes from smallest to biggest, left to right, and then from smallest to biggest, top to bottom, with the arrowhead pointing at the bottom to top with the arrowhead pointing at the top.